There we go. All right. So, bless you. So I will have you guys write those all in just a second. Okay. Let me remake this curve. So in 6.3, we're talking about something called normal distribution. So this can be applied to a lot of things in life. We're going to specifically apply it to one kind of real life example today, but basically what it's talking about is when you think about normal distribution, you will always have a mean or kind of like an average of that thing and what's called a standard deviation. So when you notate mean, that is going to be X bar is how I'll say that. It's literally an X with a bar or a line over top of it. So X bar means mean. Standard deviation is this cute little lowercase sigma, which is like an O with a curly Q on it. When we're talking about standard deviation, it's basically talking about how far away from the mean are you. So mean, and then how far away from that mean are you. So we're going to come over to this curve now. And this is called a bell curve or a normal distribution curve. We call it a bell curve because it literally looks like a bell, like a little bell that you'd ring like ding, 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 like it looks like a bell. So this is distributed symmetrically. So everything that's on the left-hand side is symmetric to things on the right-hand side. So the middle of this is where your average or X bar belongs. So every kind of like tick mark off to the left-hand side of this is called one standard deviation away. So here's your mean. We go mean minus a standard deviation or a sigma, X bar minus a sigma. And then you go mean minus 2 standard deviations. So X bar minus 2 sigma. Lastly, this last tick mark is X bar minus 3 standard deviations or X bar minus 3 sigma. Okay, so every tick mark away from the mean this way, you are subtracting your standard deviation. Every time we go to the right, we're adding a standard deviation. And I apologize, these numbers get really small over here. They're the same numbers as this side. So one standard deviation off, there are 34% of people within that standard deviation. A second one off, there's 13.5. A third, we have 2.35. And the tiny tail end is I don't know why I drew it that way. 0.15%. Okay, and again, that's symmetrical on both sides of this bell curve. So if we go the opposite way and we start adding standard deviations, it would be X bar plus sigma, X bar plus 2 sigma, and X bar plus 3 sigma. And again, those percentages also remain the same. 34, 13.5, 2.35, 0.015. No, 0.15, 0.15. Gosh, did I say that wrong? Okay. So my best example of what a bell curve is your mean is obviously in the highest part of this curve because the majority of you are at the mean. If I said that the average test score was a 19 out of 20, the majority of you got a 19. Some of you got lower than a 19. Some of you got higher than a 19. But the majority of you would have been in a 19. So this is representing how much of that average or how much of that number is occurring. So it's going to be the highest at the mean or the middle of that because you always have more people surrounding the average. So my best example is talking about basketball. So some of you are going to attack me for the players I use. But your average basketball player would be like a varsity starter or like a varsity 6-7 man or something, right? Like that's like the peak of where most people get to if they're a basketball player, that's like the peak or like the average place of where their skill level is going to be. You peak at that point and then you kind of come back down with your skill level. But an average basketball player, and I'm talking about all basketball players in the world, is going to be like the average high school player. like starter, maybe varsity, maybe not varsity, but good, not the best. Then one standard deviation off, you're gonna have maybe like a good college athlete, or maybe a really lower level pro athlete. Okay, that's gonna be that one standard deviation off. Again, like not like the best player in the world, but a college good athlete. Next standard deviation off is where you're gonna have not the top tier of players to ever exist, but some of the top players in basketball right now. So like, name some off for me. What's not a LeBron James, but is a good player? Like a D Rose. Used to be a D Rose. Yeah, Jimmy Butler, like good players, but again, they're not like the all-time like score of everyone. Okay, that's two standard deviations off. This very last one is going to be your Michael Jordans, your Kobe Bryants, your LeBron James, like the best of the best. The people that there's only like 4 of them that are ever going to exist in the world versus like 2.3 of them. We still don't have a ton of those people existing, but they exist more common than a Michael Jordan. Over here in this area, 13.5% of people would be that kind of basketball skill level. Again, that like upper tier college, upper tier even pro level versus like the average, like, yeah, you might go D3 for college or you're a really good starter in basketball in high school, but like, no, you're not pro material. So let's go the opposite way now. Okay, this is again like your average. Then we go back a notch to like a freshman in basketball that's never really played before, but like they're holding their own. They're athletic enough, like they're picking up like what a travel is, what a double dribble is, but still not the best. Then you come down to the next one where it's like third grader might be able to make a shot out of every 100 he shoots. Not the best ever, but like understands you have to kind of dribble, like understands the main parts of basketball. Out here, we have the guy that if you gave him basketball, he might punt it. Like doesn't even know what basketball is, doesn't know it exists, couldn't tell you if the word double dribble is meant to be in that sport or not. If they showed you a basketball hoop, you'd probably say like, I have no idea what that thing is, what goes inside of it. Yeah, that is way out here, okay? So again, average, and then you work your way off of that. So not many people exist in the world that literally don't even know what basketball is. Also, there's not very many Michael Jordans or Kobe Bryants in the world either. There's a lot of like average, mediocre, high school kids like that rocket are gonna make a career out of it. So that's like the best way I can explain that curve. You can apply it to lots and lots and lots of different things. This curve will stay the same. You can apply different numbers to it, but the curve itself doesn't change. These percentages that are within there will never be different. So like if you wrote this down, you will use this curve for life. I'm never going to change the numbers that are currently on it right now. Okay, let's do a little example along with it. So I'm going to move you guys. So let's go to this first example in blue. This example is a normal distribution has mean of X bar and standard deviation of sigma. All that's saying is that you're using the notation of X bar and lowercase sigma. That's all that means, which if you look at our curve, that's the notation we use. So like solid, we're rocking it. For a randomly selected X value from the distribution, find the percentage of X values that are between or greater than X bar minus 2 standard deviations, but less than X bar. Okay, so it sounds really complicated, but I promise it's not. So let's kind of pick this apart. We have to look at this as 2 different pieces for this inequality. This is the first barrier. This is the second barrier. This is where you want X to be. Okay, so it has to be in between these 2 values. So look back at your curve. And sorry, I'm trying to take you guys with me every time. So if we are trying to be between X bar minus 2 standard deviation, we just have to come back on our curve and say, well, what point is that? So we see that right here. It's like, let me put a little star there. That goes right there. Okay? That's the lower barrier. I have to be greater than that, but I can't be lower than that. So I have to stop here and go to my right, because I want to be greater than that part. My upper barrier is X bar, which is my mean right, oh, that wasn't a star, my mean right here. But that's as high as I can go. So I can go up to here and lower. So I have to think about what percentage of X values can be in between this star and in between this star. What percentages do I need to add?
13.5.
Yeah. Very good. I'm going to add up my 13.5 and my 34. So 13.5% plus 34% gives me 47.5%. Okay, so if you interpret that as an actual thing, you'd say, well, there are 47.5% of X values in between X minus 2 standard deviations and mean, just mean. Okay? All right. Questions on that one? That's the harder notation you might see. Okay, so let's go to the second example then. This one is dealing with an actual real life example, not a basketball playing one. So the blood cholesterol of a group of women are normally distributed. So that word normally distributed will be like your key word to say you're gonna use this normal curve, right? Normal curve, normally distributed. Who's gonna win? So if the blood cholesterol level readings of a group of women are normally distributed, they have a mean of 172, that's a big thing to take out, and a standard deviation, that's what SD means, of 14 milligrams a deciliter. Okay, I want you to find the following. So I have an A, B, and a C. These are all percentages that I want you to be able to find and interpret. So we're just gonna start with labeling our bell curve. Okay, before we can even interpret those values, we have to label our bell curve accordingly. So new problem, percentages all stay the same, but the way I label this will be different. So in this problem, if my mean is 172 milligrams a deciliter, where's that going to go on my bell curve? Where's that 172? Does it go here? Good, yes, it goes in the middle, right? Because X bar means mean. So if mean is X bar and my X bar, my mean is 172, it goes up from here. So my X bar is literally 172. So I'm labeling this middle hash 172. And my sigma or my standard deviation is 14. Okay, so I'm gonna bring you guys back to the curve, because this is where everything's going on at. If I follow these formulas down below, I'm gonna do the first two with you and ask you to do the rest. The first one says I have to take my X bar minus sigma, which means 172 minus 14. If I'm starting in that middle, I'm gonna take one standard deviation away. 172 minus 14, I can label this one 158. Okay, 172 minus 14, 158. What if I go one more standard deviation away? Good, I take 14 off of 158. If that doesn't settle well in your brain, go back and do the formula again. X bar is 172 minus 2 times sigma, which is 14. So now you're taking away 28 from 172. Easier way in my head would just take away 14 every single time. That would take you down to 144. Okay, I want you to fill in this last one and then all three of them over there. So label out the rest of this bell curve. Okay, we're taking this particular word problem and labeling out this bell curve for that one particular word problem. The blue is the things that will change every time. Everything in red will stay the same every single time. Yeah. Yeah, go ahead. Yeah, you can. Yeah. Because I am a today is when my scope. Oh, I'm sorry. Okay. So what did you label the rest of these? We took off another 14 to get down to 130. And then we have to go the opposite way. We start adding 14. Okay, so this way we're putting on a standard deviation. So we are adding 14 to get to 186, adding another 14 to get to 200, another 14 to get to 214. Okay, so you can follow the formulas on the bottom if that helps you. If adding, subtracting another standard deviation helps you, do it that way. It's whatever is going to be best for you. So looking back at, and I apologize, I keep flipping you guys back and forth. I don't want to make you sick. Looking back at this, we want to know what's the probability of 158 being the lowest of my X value and 186 being my highest X value. We want to know how many women are between a 158 cholesterol reading and a 186 cholesterol reading, okay? The fact of you being able to pull the percentage is half of it, and it's awesome, but you being able to interpret that is the other half of this, okay? So I recommend you guys writing these down really quick so I don't have to flip you back. So come over here, think about what's my lowest barrier. Where's that at?
Oh.
Right, oh, sorry, yeah, for this particular problem, A, 158. So my lower barrier is right here, and I'm going up from there. Good, my highest one's at 186, and I'm going down from there. So if you had to say how many percentages are in between there, I'm going from here to here, which means I'm adding up my 34 and my 34. So 34% plus 34% means 68% of women have a cholesterol reading between 158 and 186. Okay, do you understand that interpretation that goes along with it? Okay, what about the next one? What's the percentage of women that are between 186 and 200? So I can take these away now. Very good. So amount that's between 186 and 200, everything in between there is just this chunk, so 13.5. And we just pull that 13.5. So 13.5% of women will have a cholesterol reading between 186 and 200. Okay, one last one. C. Where is your X values, or how many women will be or under 186? So 186 and under. So what do I have to do for that one? This one is no longer included. I have one upper bar and then everything else. So I can go as high as 186, but I can't go any higher. But I include here all the way back to here. So this would technically be everything that I'm including. So you have to add up 34, 34, 13.5, 2.35, and 0.15. Okay, does that make sense? If you added all those up, that would be the percentage of women underneath that 186. Is it okay? Is it hard? I don't think so. I think you guys will rock this. We have one teensy tiny little thing to cover on this tomorrow, and we'll do a little bit of worksheet in class too. Do you have any questions? It's not that bad, I promise. For every single problem, you just have to make sure that you set up your curve You put all the labeling on it that you need to, and then interpreting these is really quite simple. As long as you can read inequality, you'll do amazing. All right, let me stop the recording. Is there any questions over here?